This is Jim Davidson from the Houston Space Society. I'm Gregg Maryniak from the Space Studies Institute in Princeton. That's where the beginning. Jim will be joining us in a few moments. Today we'll be talking about a project which has captured the imagination of a number of people in the space community. And it's beginning to catch fire with some non-traditional sources of support for this sort of thing. And that is the idea of a private mission, first private space expedition to another world to map the moon. Why do we want to do this sort of thing? Well, if we want to use space resources for large projects in space, this is a European solar power satellite picture. Peter, could you lower the lights to about 50%? And as we've said in sessions, and I see a lot of familiar faces, so we've heard this pitch before, it makes sense to use material that's already in space and not at the bottom of the Earth's deep gravity realm. And we're fortunate to have among this general list of resources one that's not only easy to get to and to get away from, equally important, but it's close. It's nice to talk about asteroid resources, and we're very interested in doing a lot of work on it at SSI. But the problem is the asteroids are in general about 1,000 times further away from the Earth than the Moon. And as nice as asteroid resources are, there's a lot of things you have to learn before you can use them. So we're particularly interested in adding to the traditional list of resources available in space. And it turns out that our nearest neighbor, the Moon, still holds a lot of mystery. We look forward to using the Moon for science, as a base for exploration in other places. We hope to see commercial activity on our little planet. And thanks to Apollo, we know quite a lot about certain parts of the Moon. We know that, in general, on average, this is a pie graph of what materials are available, and we know that there are parts per million quantities of substances like hydrogen, helium, carbon, which are the result of solar wind implantation. And people are talking about exploiting that level of resources, but it's very difficult. Getting a thimbleful of hydrogen out of a volume about the size of this room, perhaps, isn't all that wonderful and easy a thing to do. And we know that 40% of the Moon is roughly oxygen, but we have yet to find much hydrogen aside from this parts per million sort of activity. And even the oxygen that's there, and while it's worth getting it out of the rocks, it's difficult to get out of the rocks. And people who are now getting into the business of chemical processing, various kinds of processing of lunar soil, something we've been doing at SSI for about 14 years now, in various forms, are learning just how difficult it is. There's a lot of NASA interest, for example, in the ilmenite process. But it's interesting to watch. They're suddenly discovering, gee, there's not nearly as much ilmenite as you thought. And it's a form of ilmenite that people are playing with on the Earth is mostly not, but it's not on the Moon. And so there's likely to be a lot of changes in people's thought.
Can you focus on this?
Yeah, Dennis, can you give me a focus on that, in that location? It'd sure be nice to find a source of material that could provide us with the hydrogen and the oxygen, which form the basis of chemical rocket propulsion. And we hope, we believe that there's a gambler's chance that sometime in the fairly near future, a scene like this will take place in the lunar poles. We will find volatile substances, including water ice, trapped at the poles of the Moon. Why might there be water at the poles of the Moon? The reason is that, unlike the Earth, which has an axis of rotation inclined 23.5 degrees to the plane of the ecliptic, the Moon's axis of rotation is only inclined 1.5 degrees. What that means is that the Moon does not have colder summers. We don't have the seasons that we have here on the theorized for over 30 years now that the moon may cold trap volatile substances like hydrogen and water, in fact, which are the result of outgassing from the moon, which are the result of delivery of volatiles to the moon by comet materials, asteroid materials, that have impacted over time. But nobody knows for sure. Now, why do we care so much about finding water? Why would it make a difference? Well, we talked about propellant, and that's the first thing that most people think about. And it's clearly useful for life support, we're all used to having water. And anything you need the oxygen for, it's nice if you don't have to fight chemical bonds of the lunar rocks to get the oxygen out. But water itself is one of the most important substances that we use for all kinds of processes on the Earth. We use it for example, to dissipate heat in radiation systems. We use it for chemical regions, mainly. Almost all kinds of chemical processing of water we get. And a big one in the lunar case that's interesting is reactants for power storage. Unless you are dependent on nuclear systems, one of the better ways, and none of the ways are all that terribly good, but one of the better ways to store electrical power is to break water down into hydrogen and oxygen and combine them in fuel cells. But if you start to look at that, you realize that the mass of the reactants is considerable in that kind of system. So it would be really delightful to find water if it's there. And it would be something like finding the Northwest Passage, in that it would greatly accelerate the pace, capability of space development. But there's a small problem. The small problem is we don't know if there's any water there. This is a controversial subject. Don't let anybody fool you. For every person who says there might be water ice there, there's one or maybe two people that say, nah, there's no water there. But nobody really knows. The bottom line is people simply don't know. Now that's kind of curious. Why is it that we don't know? We spent a fair amount of money on Apollo. We've flown lunar orbiters. We take pictures of the poles of the moon. Why is it that we don't know? Well, the reason is that our Apollo flights, which carry the kind of remote sensing equipment capable of detecting hydrogen, for example, were only flown in equatorial orbits. There was a plan, and you know there are 3 Saturn V's lining the sides. Various speakers have alluded to them in the last couple of days. And the odds are good that had all those missions that were planned and flown, one or more would have flown in polar orbit and carried, in fact, a device that we hope to fly, which may have detected water at the poles of the moon. But this is the extent, on the near side, of the overflights of gamma ray spectroscopy that was done during the Apollo program. So what we really need is we're not only interested in looking for water, although we're very interested in that, but we're interested in completing the chemical map of the moon, because now it's very sparse. And in fact, the overflights in these areas amount to a very small amount of observing time with a kind of a device that gets better data with more time over a given area of the moon. So it would be nice to have even the areas that are shaded in blue detailed more than we have today. I'd like to spend the remaining time that we have this morning telling you, from my perspective, the Lunar Prospector saga, letting you know what has happened historically with it and where we're going right now. And I'll be followed by Jim French, who described the spacecraft. Jim is the project manager for the Lunar Prospector program. In 1985, after a number of years of discussion and thinking about this problem, people like Dr. Gerard O'Neill, the founder of the Space Studies Institute, have been writing about the possibility of finding useful materials at the poles and otherwise learning more about the moon than we brought back from Apollo. We decided that this was a sufficiently important subject that we would seek out an expert to look at the possibility of a relatively small dedicated space probe to find the answer to these questions. Now, you have to keep in mind the history of lunar polar orbiting probes in the world, not just in the United States. And that is that even during the Apollo program, there were discussions about flying a mission of this sort. And in fact, many people believed that this was a mission that was right around the corner. And they've been believing it for over 20 years. And old NASA hands at this point have been saying to us, look, don't believe that it's ever going to happen within our organization. Even if they say it's going to happen, you guys just keep on trucking because there's no guarantee. In our early stages of thinking about this, we were still interested in trying to convince the government, basically, to fly a relatively modest, simple mission, not a $500 million mission, but a small number of tens of billions of dollars, if that was feasible, to try to find out the answer to the question of water, whether or not there's water for poles, and generally flesh out the lunar map. So we asked around, and we went to people at JPL who had been in the lunar business for many years, who were diverse in the entire international picture, and the British had gone through this with the mission of Apollo, the Russians had flirted with lunar polar probes for many years. And our contacts pointed to one man as a person who would be ideal to study this problem, to tell us what would be involved in the lowest cost effort that might be taken by the government. And that was Jim French. Jim will probably tell you a little bit about that as he discusses the program today. And we timed Jim's work as part of a package of studies that the Space Studies Institute was preparing, investigations that were designed to influence the President's National Commission on Space. Chairman Tom Paine, Dr. O'Neill, and Dr. David Webb are all involved with SSI as directors or officers. And so we had their ear, but we wanted to convince them by hard data that this was a useful program and a critical one. And so some of the work you see around here on experimental tanks and Jim's work and a group of other things were prepared and presented as testimony both to the staff and to the entire National Commission on Space by their invitation. And the result of that was that indeed the commissioners did get very interested in the potential of this. And this is what they said in their report, Pioneering the Space Frontier. They said it's a first priority to search for these potential molecules. So that took place in the 1985 and 1986 time frame. And in 1986, we were feeling kind of good. The commission had said this, and we were excited about it. And we thought, this is great. Maybe something will happen. And as you all know, nothing in particular happened. In 1987, therefore, we decided to try to do more agitation and see what we could do. And we went back to JPL because we had heard about an interesting idea, which this picture does not show. I think I'll go back just to not confuse people coming in. But the idea was to fly a small spacecraft that would be capable of being jammed into a getaway special canister on a space shuttle. And it would spring out of this canister and under ion drive propulsion, spiral out of low Earth orbit, transfer to the lunar sphere of influence, and spiral down into low orbit around the moon. And this was a project based in part on desperation. JPL had not had a launch in almost 10 years of any of their equipment. And a group of people that were frustrated was all get out and said, we can't get any access to space. But there are these getaway special cans. And it was a very interesting idea. It's a little bit ahead of its time, and it was a little overly ambitious in that it had to stuff a huge solar array into a very small area, and solar arrays, even modestly packaged, are always a big worry for commercial satellites, for example. And it was also a mass problem. It's difficult to do things like fit all the power conditioning in this little spacecraft. But it was a very interesting idea, and it captured a lot of people's attention. And it captured our attention to the point that we went to brief the then administrator of NASA, Dr. Jim Fletcher. And we did that in mid-1987 time frame. And we learned more about it and discovered that there were some Atlas E rockets that were potentially available for launching small spacecraft. And in fact, Dr. Fletcher was sufficiently interested in this that he made a trip from NASA headquarters right after speaking with us to JPL in So we began to see some government looks into it and actually a little bit of money spent in examining the idea of a small dedicated probe with maybe just one or two instruments on it. Instead of a Cadillac space probe approach like Lunar Observer would be, which is very nice, and we should all support it. And we, in fact, at SSI support it very strongly. But we said, let's get something quick now, get the answer now. We were particularly interested in doing this because of the discussions that were going on following the President's National Commission on Space. And there was, the Office of Exploration was beginning to get started. Some right to do a report at the time. And there was a discussion about what was called the pathway decision. The pathway decision was, we're going to figure out how we go forward in space. Are we going to go to Mars via the moon? Are we going to go to Sandusky via Cleveland? What are we going to do? And we felt that if we could get the answer to the question of the composition of the moon, especially in the polar regions, that we might have a strong ability to positively provide ammunition for making a sensible decision. Those of you who were around yesterday, heard what we think about just whizzing off to Mars as a mad dash. We very strongly believe that the moon is a logical step and gives us a doorway to the whole solar system, not just the one other planet's deep gravity well. So once again we learned that the government, while it was interested, was fairly entrenched in their present way of thinking. Particularly, one thing that we learned was space resource prospecting bears little or no relation to the priorities of the space science community, which are the people that have the budgets for planetary exploration. To be blunt about it, they don't care about space resources at all. They're interested in finding out what makes the universe tick. And it happens to give you some chemical composition, which it does, and they need it as information, fine. But they don't care one little bit about space resources or using space resources, because it's not their job. And it's perfectly logical that they shouldn't care about it all that much from their point of view. So, in 1988, we began to contemplate networking people that we knew in the space science community to sort of do a feasibility study of doing a private venture, privately fly a program on the whole space. And that resulted in a number of activities, and Dr. Gabe Canuck was coordinating this activity for the Institute at the time. And she liaised with Jim Davidson's group, the Houston Space Society, and we had been stopping for this for some time and helped to get a fire lit under a number of people that got very interested in this kind of mission. And Jim put together a very good conference, which we'll probably talk about too, in Houston, and gathered together people from the Houston community, the Johnson Space Center community, interested in doing this kind of approach. And we invited people from that Jim had helped intake and that Gabe had helped intake to a meeting about 1 year ago in Princeton, New Jersey, where we basically hammered out the rough specifications for a lunar prospector. And the idea was that we would fly a simple probe that could get a piggyback launch, probably on an expendable vehicle, because we don't think we can afford the integration costs attending to going on shuttle and all the huge list of no-nos, things you can't do. And these pictures were done by SSI artist Ron Jones, actually, for photo montages of models and things. And in this particular picture, it shows a sort of generic lunar prospector getting a ride on an Atlas E. But the main feature of it is that it's a spinning spacecraft. It's got some instruments out on booms. And in particular, it has a cylindrical gadget, which is called a gamma ray spectrometer. Gamma ray spectrometer is a chunk of sodium iodide crystal with photo multiplier tubes on both ends. And when gamma rays come off the surface of the moon, they cause essentially scintillations, light flashes inside the crystal. And by measuring the energy of the light with these photo multiplier tubes, you can find out what kind of gamma rays, what energy gamma rays have been striking the crystal. And these gamma rays are the result of cosmic ray bombardment of the moon and of the nuclei of atoms in the moon. And depending on what kind of nuclei is agitated, you get a certain energy gamma ray. So it's most sense for materials in. Now it turns out there is a gamma ray spectrometer which would have flown to the moon had all the power missions taken place. And it exists on a shelf basically at the Jet Propulsion Laboratory. And during 1989, especially the latter part of 1989, we spent a considerable amount of effort talking with some friendly members of Congress and asked them to approach NASA for us, send a letter to NASA, requesting that the gamma ray spectrometer, the actual flight article, be donated to this program. In fact, NASA responded positively. Admiral Truly, after some interesting interactions, said yes. And I'm happy to report that we're about a 2-inch putt away from signing a legal document, which has grown from a 2-page letter agreement into about a 24-page boilerplate legal document, which is very favorable, very reasonable. And I'm trying to say that NASA's been at all reasonable and quite helpful. And in fact, NASA has appointed a liaison within headquarters to work with us on the project, Dr. Joe Alexander, he's an associate professor. And so we're now at the stage where we're just about ready to receive the instrument and to begin a program of refurbishment. The other thing that started as a result of the meeting in May was we put together, with the help of a large group of people in Houston, which has now subsequently, for tax purposes, registered itself as a nonprofit corporation called Lunar Exploration Incorporated, which is now part of a two-entity consortium. It's called the Lunar Prospector Consortium. The LAR people had put together an RFP, a request for proposals, for the design of the actual spacecraft. And we put that out for bids or for responses, and we got a number of excellent responses from satellite manufacturers across the country. And we selected a contractor who's right here in the Los Angeles area called Omni Systems Incorporated, which is made up largely of expatriates from Hughes Corporation. They're a good match for us because we want a spinner and they like to make spinners. We're crazy and they're crazy. And I'm happy to report that the critical design review, which is basically the end review of the spacecraft design process for this phase, will take place in several weeks, on June 16th. So we're very close now to having the final spacecraft design and a full-scale mock-up. And we're taking these tools on the road, so to speak, and we've now begun a fairly lengthy and expensive process of trying to raise the approximately $15 million that we expect to spend on this mission, which is exclusive of launch costs. And in addition, I think I'll wrap up here because I'm going a little over time. We are actively pursuing a piggyback launch for this spacecraft. And one of the most exciting things that has happened in the last few months is that we have had an ongoing dialogue with the Soviet Union. And they have basically come to us. We were talking with them about some completely different kinds of matters. And they have come to us and made us what I'll call a squishy offer, but it's an offer. And they have, the Soviets have reported to the U.S. Space Trade Press, I'm sure that was about a 3/4-page article in Space News, which surprised me, that they're offering us a lift on a proton. And the time scale for this ride is quite good. It would be during International Space Year, which is our target for launch. That would be 1992. International Space Year is actually a multi-year process, and things may change a little bit depending on the nature of the Soviet launch. There's no guarantee that we'll in fact get the Soviet launch. But it's had another interesting effect. The fact of this offer has now spread through the community, and it's caused some of our friendly federal officials to come to us and say, gee, we really ought to be helping you folks a little bit more. And all in a very, very positive kind of way. showable designs, some real things to show people, and a serious program, we'll make it possible for us to secure the funding that it takes. But I want to challenge you, because we're all members of the space enthusiast community. And that is this: the Space Studies Institute has pretty much borne the brunt of this program to date. In fact, we have spent, if you sum up all the time, the expenses, and the cost of the design project, the design work that we're paying in contracts, we will have spent almost $500,000 on this program over the life of the program. And we've had a lot of very friendly noises from the space enthusiast community, of which we're part, saying, this is a great program. You guys are really showing a new model of ways to do business. And I want to challenge you, if you think it's a good program, if you think it's goofy, or you think it's not the right thing to do, no problem, that's your right. But if you think it's good, and if you think private outfits and private individuals ought to strive to do missions in space, then I ask you, when you go home, or better yet, even before you go home, write a check, send money, because this is a very costly process, and we've got to keep fuel in the bank, fuel in the tank, to keep this thing moving along. And it's been by dint of efforts of folks like Jim's group in Houston, which you know, office, which they sponsored for our Houston team of engineers and scientists, and the True Blue members of the Space Studies Institute who contributed to keep this project going, that we've been able to get as far as we have in the past year. It's pretty amazing. A lot of people said we'd never get this far. We know we're just beginning, but we're plugging along. So if you believe in it, then really do something about it. And I mean do something substantial. Help us along, because we've put in the equivalent of almost $1,000. We've put in hundreds of dollars per member of our organization to bring this thing along. We need your help. So if you like it, really do something about it. Let's not come away, we've said this a few times, other people have said that at these conferences, let's not just go to these conferences for a warm, fuzzy feeling. I hope you come and you get supercharged and you say, let's do something, let's change the world. Because we think this could change the world. If we're successful, and if we're successful, we'll get a chemical map of the moon. If we're lucky, our gambler's chance will pay off, and we'll get a 25-year shortcut to the humanization of space. So let's try. Thanks. I'll be around. I'll tell you what. I'll take questions at the end because I've gone over my time, and I'd like to turn over the forum now to Jim French. Where are you, Jim? There's Jim. There he is. Okay. And I think we'll let Jim introduce himself, because I'm not sure how much he's willing to say about all the manifold activities he's doing.
My name is pretty frequently been mentioned, is Jim French. I got involved in this as I first doing a preliminary study of what might be minimum cost lunar orbiter mission, and that willy-nilly has led us to where we are now. One various and sundry other things. I did spend about 19 years at JPL, and among the many things I worked on there, at least one of the things was looking at some very low-cost missions, including an inexpensive lunar orbiter mission, which in fact was so inexpensive nobody was interested in it. It didn't keep enough people occupied for long enough. So at least I can claim that I've had the right orientation. What I'm going to do here is run through the mission in a little more detail, perhaps, than Gregg did, and then tell you about the spacecraft design as it's evolving. And I don't have any real fancy graphics of the spacecraft itself, for the reason that it is still evolving. As Gregg says, the final design review of this preliminary study phase is coming up next month, and sometime after that we'll have all the fancy graphics. But right now we're not quite to that stage yet, so you're going to have to settle for some fairly simple ones. I'll start out, however, with a slide projector, and
moon, on the other hand, relative to the ecliptic plane, has a very small tilt, 3.5. And that means that there is substantial geographic relief in the polar regions, which there is by inspection. Then there could well be regions where the sun never shines and has perhaps not shined over geological periods of time, tens and hundreds of millions of years, maybe even billions, depending on what you want to believe about the gymnastics the moon may have gone through. Now, our lunar samples and our observations of the moon to date show no water whatsoever. There's no sign that any water has ever been on the surface of the moon. So you may well ask, where would this water and possibly other volatile materials such as carbon dioxide, ammonia, and so on, that could be cold trapped in these polar dark locations, where might that have come from? One theory says from cometary impact. There, go back to the basic formation of the solar system, the impact of planetesimals formed the various bodies, and later on residual small cometary bodies would continue impacting and still do so today. These bodies are predominantly water, and if they haven't been in the inner solar system, others do contain substantial amounts of other volatile materials. One impact, these would be vaporized, in essence giving the moon a temporary atmosphere due to its gravity, or it all escaped due to the solar pressure or heating. Some of it would have migrated to the poles and been cold trapped in these dark regions. Now, that is by no means a non-controversial theory. There are lots of reputable scientists to say it ain't so. But we've never been to the poles to really look. Gregg showed you this one. That shows the ground track of the Apollo missions that did carry the gamma ray spec. And I should point out that the time that they spent in lunar orbit was sufficiently short that, as I'll talk about the resolution of these instruments earlier, they wouldn't have found any water if there had been bubbles of it on the surface down there. Another thing you need is longevity, long periods of time in orbit. Apollo never spent more than on the order of 10 days or so, maybe even less than that in lunar orbit. So they didn't have a chance if R.A. Ebrium had really been an ocean. They probably protected it. What we're going to do is put our vehicle in forward orbit. Since the most likely location for these volatile materials is the polar regions, obviously we will get the best possible look at the poles. It works out nicely to our advantage. And to be in orbit and to go over the poles, you've got to be in an orbit that is what we call polar, that is at a high inclination that takes you to 80, 90 degrees latitude on whatever body you're orbiting. The advantage of that is if, let us say, you're in a pure polar orbit, then every orbit you go over the North Pole, and half a period later you go over the South Pole. So you are building up your observation time in the polar regions very, very substantially relative to what you do at the equator, where each orbit is displaced from the previous orbit by the amount that the moon rotated, and it's in essence 2 weeks before you repeat the orbital track again. From one orbit to the next time you come exactly over that path, all over the opposite sense, because you're on the other side of the sun. It's 2 weeks. So it takes you a long time to build up substantial observational time at the equator. But we'll pass the poles at, say, the same pole every 118 minutes in the polar slope over orbit. However, the sensitivity of a gamma ray spec is unfortunately sufficiently low that we still require an extensive amount of observation time, on the order of about 100 hours accumulated time, to really have a high degree of probability of detecting water, especially if it's rather diffusely implanted into the surface material as opposed to being actual snow drifts or ice strips, if you look at it that way. What it works out is we need observation periods on the order of a year. I won't go into all the assumptions that are implicit in that. And in fact, a year and a half would be better. In fact, the thing about a gamma ray spectrometer is there ain't no such thing as too much data. The longer you look, the better your resolution gets. Obviously, there's some practical limit, but we like to stay in orbit, taking observations as long as we possibly can to improve our knowledge of poles and, of course, to build up the observational data in the other regions. Talk a little bit about the instrument payload of this spacecraft. We referred to the gamma ray spectrometer several times. That is the primary instrument. It detects gamma rays that are given off as a result of cosmic ray impact on the atomic constituents on the surface. Each one of them gives off a gamma ray that's of a specific intensity and frequency that identifies the particular material that emitted gamma. That doesn't work real well, unfortunately, for water, where you're really seeing the hydrogen. But what does work well is that you can also detect neutrons. Bombard hydrogen and get a certain amount of neutrons. Well, all these particles are few and far between. That's why it takes a long time to build up the required observational data. So we proposed to modify the Apollo gamma ray spec by the addition of a neutron detector, basically another detector that rides in the same instrument. It's a relatively simple modification. Another instrument that will ride on board is an alpha particle spectrometer, or alpha ray spectrometer, if you will. It looks for alpha particles, that is, fully ionized helium nuclei, that are also given off, particularly by radioactive materials on the surface, such as radioactive isotopes of potassium, mostly uranium, and actinium series, I believe, will also give these off. And finally, that's a new instrument that is being devised strictly for this mission and is relatively simple. It'll be the first time, I believe, such a thing is going around. Final instrument is similar, in fact almost identical, except built with commercial parts rather than space qualified parts, to an instrument that will fly on the Mars Observer mission. That's an electron reflectometer and magnetometer system that really doesn't, it's one instrument that doesn't specifically look for constituents of the lunar surface. What it really is looking for is local magnetic anomalies, since as we know the moon does not have a magnetic field in the global sense that the Earth does. There are, however, local magnetic areas on the surface which may be due to impact, residual magnetism from the moon's form, or whatever. The interaction between those and the ions, electrons, and solar wind are of substantial interest, and that's the purpose of the electron reflectometer magnetometer. A mission, I'm sorry, I was just going to show for contrast, that's one variation of what the NASA JPL version of the Lunar Polar Orbiter might look like. It's loaded down with instruments, and that's fine, I'm not putting it down, I'm just pointing out the contrast between a great big government-funded spacecraft that tries to do everything, a little bitty spacecraft like the one that we're flying here. The launch would take place on some kind of conventional expendable launch vehicle, simply because of the complexities involved in getting on board the shuttle. We don't think that's practical within our kind of budget. This is another variation on the stuff that Gregg showed about placing the vehicle in orbit on an Atlas-E. It's of substantial importance to us how we're launched, in the sense that whether we go into low Earth orbit, geostationary transfer orbit, that is an elliptical orbit with a low periapsis and an apoapsis out of geostationary altitude, or about 40,000 kilometers, or if we might really luck out and get a ride actually into lunar transfer orbit. That's of substantial significance, as I'll touch on when we talk about the spacecraft later. The Atlas-E would simply put us into low Earth orbit, as shown here, and we'd have to make the rest of the trip on our own, which means a substantial increase in propulsion capability. But in any case, we would wind up in orbit. You can see the three instruments deployed in this illustration, which, as Gregg mentioned, is an older one of the sort of the additional concept that led us into these studies. Flip on the overhead projector. Let's talk about the real spacecraft now. It's not a real good drawing. As I said, we're not that far along, and forgive the notation to tell what color it is, because that was really instructions to a model maker. We have both a full-scale model and some 10-scale models of the spacecraft being built. One of the differences from the previous version that you saw, that previous one had deployable solar panels, flat blue panels that you saw. It was a spinner. This one is also a spinner, but we have gone to the design of having the solar arrays on the exterior drum surface of the spacecraft. The bad news about that is that since only one side of the spacecraft can be in the sun at any given time, it takes slightly more than twice as many solar cells as it does otherwise. Solar cells aren't cheap, so we're trying to buy any. The other virtue of it, however, is you don't have to deploy anything. You move them on there, build it, and they're there. You don't have to worry about deployment, shadowing, and so on. We figure we have enough trouble deploying the instruments out of those booms. The instruments are on booms, incidentally, because none of them like to be near anything. The gamma ray spectrometer detects any mass that's in the vicinity. It even detects itself, and it detects its own spacecraft and anything else that happens to be around. So you want to get it as far away from the mass of the spacecraft as possible, just to get rid of the background noise, which you have to subtract in any case to be able to detect what you're really looking for. The alpha has similar problems. That's the spherical job over the lower left as you view it. And of course, the magnetometers will be sensitive to magnetic fields generated in the spacecraft, and the spacecraft does generate magnetic fields. Now it's got electrons going through its surface. The spacecraft that you see there will weigh empty, that is without propellants on board, on the order of 120 kilograms, say on the order of 250, 260 pounds. That at least is our target. The maximum weight that we're targeting right now, or maximum mass, is around 322 kilograms, fully loaded with propellant. And how much it actually weighs depends a lot on the ride, as I mentioned earlier. In fact, let's talk about that right now. To place the spacecraft into low circular lunar orbit from the lunar transfer trajectory requires about 820 meters per second. We have allocated 90 meters per second of delta V, or velocity change, in the trip to the moon to provide for mid-course corrections. We shouldn't need that much, but it's a lot better to have it not needed than the other way around. And we have allocated 490 meters per second for orbit maintenance. The moon is a very irregular object. It's egg-shaped in the first place due to distortion from the Earth's gravitational attraction. Plus, it's loaded with mass concentrations, so-called masscons, that confused the issue for the Apollo missions in the early days. If you leave a spacecraft in low Earth orbit around the moon and don't do anything about it, it will crash in a matter of a few months due simply to the irregular gravitational field. So we've allocated a very substantial amount of propellant, much more than we should need theoretically for 1 year, to maintain that orbit. So whatever we don't use in the first year simply means that there's that much longer we can keep the spacecraft operating before it crashes. Or if we for some reason wish to do so, we can bump it up into a higher, more stable orbit once we've taken sufficient data. Adding all those up gives a delta V velocity change capability on the baseline spacecraft of 1,400 meters per second. That will be the minimum capability of the spacecraft. If we wind up in a geostationary transfer orbit, that is, as I said, the elliptical orbit that has its low end at, say, a couple hundred miles, and its high end at 22,000 miles, then the additional delta V to get us from there into the translunar orbit, translunar orbit is 920 meters per second. We could achieve that in the same spacecraft simply by loading the propellant tanks all the way up and providing a regulated pressure system, a low-down system that we're using now. I won't try to explain that because I don't have time. If somebody wants to talk about the propulsion system later, I'll be glad to do so. If we wind up, and that we can load that much into the spacecraft without changing its external appearance as seen there. If we are left in low Earth orbit, then the required delta V for translunar injection is 3,600 meters per second. This is not a trivial amount and would require some additional stage, either a solid stage or additional liquid propellant stage on the spacecraft there. So we're obviously very interested in getting it pinned down as to what kind of ride we're going to get. The propulsion system that we're going to use in this spacecraft is bipropellant storable nitrogen tetroxide and monomethyl hydrazine. We had started out with the idea of using a monopropellant system and decided that there were enough advantages with BiCrop in terms of performance that it was worth the additional complexity. For the radio buffs in the crowd, I'll talk a little bit about the communication system. The device sticking straight up out of the center toward the top there is the antenna. We have an Omni antenna, that is the one that puts out pretty yearly hemispherical pattern, and a medium gain antenna which puts out more of a donut-shaped pattern for higher data rates when we're out at the moon, both of them mounted on that shaft. The data rate coming back from the moon will be 10 kilobits per second, of which about 8 is science data, and the remainder, about 2 kilobits is engineering data, and about a few hundred bits are just housekeeping that let us figure out what bit is what when it gets back here. We don't have to have the engineering or the science data on. We can't just shut it down when we're not near the moon and get engineering all the way back. For those of you who are into these things, we broadcast about 8 watts broadcast power, and we got a 4.8 dB margin from the moon at the full data rate to a 10-meter diameter dish on the ground. There are lots of 10-meter diameter dishes around, Landsat and other purposes. We'll be operating in S-band, which is in the say in the range of 2 to 2.3 gigahertz. Obviously, that has to be defined. We have power level of the total spacecraft at the end of life, that is 1 year in orbit, allowing for degradation of the solar rays and so on, is 175 watts. So it's not a big power hog. Fortunately, none of these require a great deal of power. The worst problem that we've got, as far as I can see, overlooking funding, which is not my bag, is surviving the eclipse. Because if you stay in orbit around the moon for 2 years, you will go through 2 eclipses of the moon from Earth. Solar eclipses are very rare, relatively speaking, but lunar eclipses happen twice a year, whether you need them or not. During that period, of course, the spacecraft, since it's in orbit around the moon, will be shadowed. What we're faced with is about 3.5 hours of no sun at all while the moon is in the umbra of the Earth, with a lead-in period and an exit period of about 1.7 hours before and after when we'll be in the penumbra, that is to say, partially illuminated. That's going to be real tough. We have enough battery power to survive it, but we're going to have to be powered way down. We've got to orient the orbit properly to minimize the amount of time that we spend in the shadow. That's probably the single most critical issue that we're facing that we absolutely can't do anything about. Mother Nature, we just got to design to live with it. Okay, as the final point, let me talk a little bit about well, I should mention the propulsion system. This one shows a big thruster at the center there, a 100-pounder for lunar orbit insertion. It's not clear whether we'll fly that or not. 2 little ones on either side are 5-pounders or 22 newtons for those units. And it looks like we can do the orbit insertion with those thrusters. It takes longer, it's a much longer burn time. We probably go first into the elliptical orbit and then burn again later into the circular rise. So you can save a lot of weight and a lot of cost if we want to have to fly a big thruster. Attitude control is carried out by small 4.5 Newton or 1-pound thrusters that are radially located up on the sides of the drum there for tipping the spin axis of the spacecraft appropriately for these maneuvers and also get it set up in the right attitude in the first place. Okay, I told you that we needed 100 hours of accumulated observation time in the cold. Talk a little bit about probabilities of detection. Without modifying the gamma ray spectrometer, that is, without adding the neutron feature, we would require a feature on the order of 10 meters in diameter to be of water to be able to detect it. And if the weight percent is only 0.8% water, that is to say the rest of it's rock with just a little bit of water in there. The more water involved, the better off we are. If we incorporate the neutron spectrometer, then the detectability goes up substantially to about we can detect as low as 0.2%. That compares pretty favorably with one that the NASA spacecraft would fly, which uses a new germanium detector, new technology relative to the sodium iodide detector that we're going to have. But that gives you a factor of 2 improvement down to 1/10%. But the point you should take away from this is that this is a difficult mission. It's not easy to detect that water, especially if it's heavily intermixed and with surface material and widely dispersed. The reason I issue that cautionary note is we have to face the fact that we may not detect it. And I would caution people not to get so wrapped around the axle about detecting water that if we don't find it, everybody says the mission was a failure. We could suffer from the same problem that NASA and JPL suffered with on the Viking landers, wrapped up publicizing the search for life, that when we didn't find any, some of the editorial writers around the country were shrieking that the entire mission was a total failure. In fact, it was one of the most brilliant successes in our planetary program. Finding or not finding life was only one aspect of it. Similarly, finding or not finding water on the lunar surface, despite its vast importance, is only one aspect of this mission. We need a compositional map of the surface of the moon. Whether NASA flies their mission or not, this one is a valuable and valid mission that will bring back good data, and if NASA flies theirs later, will help them refine their data. Like I said, there's no such thing as having too much of the kind of information we're gathering. So the longer we can stay up there, the more we can do, the more data we can gather, the more we're going to improve our understanding of the moon. It's important to know where the various types of lunar material that we're familiar with are situated. For example, I believe I'm correct in saying that if you believe in harvesting helium-3 from the moon for use in thermonuclear reactors someday, there tends to be more helium-3 associated with the titanium-rich basaltic rock at the surface than with other kinds of rocks. So if you're going to set up your helium-3 harvesting facility, it'd be nice to know where the titanium-rich materials are. If there are radioactive materials, for example, it might be most interesting to know if there are concentrations of that sort. Concentrations of any material are going to make things a lot easier in terms of the way of using lunar materials than if we have to do everything through the dispersed medium regularly. So this is an important mission. Water would be a tremendous bonus if we can find it. But if it's not there, if somebody told me today that we've written and blowing letters in the air that there ain't no water in the poles, we'd still want to do this mission. Because we're going to make use of the water. We've got to understand it better. And our knowledge of the global composition of that body is woefully lacking. It's time to do something about it. Thank you.
I think most of you have a sense of why this mission is important. This is the first scientific mission of its type that's directed towards studying resource utilization. What resources are really there that we could go and utilize to create the kind of spacefaring civilization that most of us would like to see take place. I got kind of interested in this in September of 1988. The transition committee of the National Space Society Chapters Assembly was meeting in New Orleans, and a representative from a launch company was there and indicated that their company might be willing to donate a launch if there activity that would indicate that this is something that the space movement was behind, that a lot of people were working on, the mission would actually happen. So we decided to organize a conference to bring together all of the organizations that had an interest in this program. People like Peter Cook's Milwaukee Lunar Reclamation Society, Houston Space Society, Extraterrestrial Materials Inc., which was Gregg Maryniak's group, and a bunch of other organizations. In fact, over here on this table, there's a document signed by representatives of 27 different organizations. The point being that we recognized, and we in fact stated in this document in March of '89, that for this mission to succeed, it's going to really take focused effort and a unified framework for everyone to work together. The leadership of the Space Studies Institute has been essential for making this project work. And to have a bunch of other organizations supporting the Space Studies Institute is going to make their job a lot easier. They have a limited number of people involved in the Institute, a limited number of senior associates, and there are many space organizations that are interested in this activity that can support it. Some of the things we've done as the Lunar Prospector team since March of '89, in June of '89, we donated a surface barrier detector for the alpha particle spectrometer, which is being put together at a laboratory in Houston. In September of '89, we received approval of a loan grant from the Chicago Space Development Conference, last year's version of this conference you're at. We also arranged for the Houston Space Society to obtain a percentage of the funds they were raising from the fundraiser in Houston. In December of '89, we donated the funds that were necessary to provide utilization of the Clear Lake Area Applied Technology Center for the project. This provided access for the science team and the engineering team to computer-aided design and computer-aided manufacturing equipment, computer animation software, a variety of peripherals, plotters, and so forth, and super mini and mainframe computer capabilities. In February of 1990, we furnished the Office of Lunar Explorations, Inc., so that they would have desks and chairs and filing cabinets and all the other essential accessories. And we've continued to make donations to the Institute and to Lunar Explorations to support their immediate cash needs. Before I talk about who we are that we're doing this, I'd like to indicate a few things in 4 basic areas that I think you could do if you were interested. If you were interested in this mission and wanted to see it fly. What can you do? You could donate money to the Space Studies Institute. One of the best ways to do that is as a senior associate, and I think Randy Giganti or Gregg Maryniak can tell you a lot about the benefits of that program. You could donate money to the Lunar Prospector team, and we'd see that it got to the right people. If you want a tangible return on your donation, there's a second way you can contribute, and that's by buying merchandise. For anywhere from $100 to $610, they have a variety of things that you can take home with you that will indicate that you supported this program. And a lot of people like something for something. You can also volunteer your time. If you have an organization, a chapter of the National Space Society or some other group, you'd like to sell merchandise on consignment, we can wrap some of this up and you can take it back to your group. I think another important way to volunteer time would be to recruit other members of the Space Studies Institute Senior Associates group. I'm a member of that august body of dedicated Institute supporters, and I think having more of those types of supporters pledging money over a long period of time to the Institute helps their finances in a way that no other form of giving really can. And finally, fourth and finally, there's a painting in the back, the original by Doug McLeod of Lunar Prospector at the Moon, painted for last year's conference. Current bid on that is $600, and if you know of anyone, or if you are someone who'd like to bid on that, we're having a silent auction, and the proceeds will benefit the Lunar Prospector mission. came to the Lunar Polar Pro Conference, in signing this document, the Citizen Initiative, said that this mission was important. And the reason they decided it was important was because it has an opportunity to significantly accelerate, by doing this mission, accelerate the time frame that it's going to take to have a civilization out in space, to be able to use lunar resources, to help use space to solve problems on Earth, and to help create the kind of cities in space and communities, and the possibility of going out into the universe that most of us here in this room want to see. We fly this mission in 1992. It will send a major signal to politicians, to the corporations, to just about everybody involved in space, that the people of this country and the people of the world are interested in going out there and exploring. They're willing to put up their own money for it. They're willing to do something. Now, I want you to each think about this next question. Who is in this room? Who are you people? The National Space Society and the California Space Development Council called this conference, and hundreds of people showed up. And they announced this program. You are the people who showed up. This is the program about Lunar Prospector. This is about a major mission to fundamentally increase our knowledge of the moon for resource utilization purposes. This is the mission that has, I think, the greatest chance of changing where we are in the world about space. People in this room walk out of here without having made a contribution. I want it to be a very serious and very deliberate decision on your parts that this mission isn't something you support. I think just the contrary. You showed up here because you're the people who care about this mission. You wanted to find out more about it, and you wanted to do something about it. And I suggest you take the opportunity at this time to do something. Thank you.
We'll take questions out in the hall, but I'd like to do one thing before we do that, and that is to thank Jim Davidson publicly for all the help from the Houston Space Society. I think he's been a great representative of how NSS can really help push this along. The other thing I want to ask you to do is find Tim Kiger, who's around there. He's a guy who works for Congressman Rohrabacher. He was saying yesterday that he doesn't get any letters on space. But even though he doesn't get any letters, in fact, there he is in the back there. Hey, Kiger, come in here. Tim Kiger, come in, please. I want you to give this man a giant round of applause. He's the guy that lassoed Rohrabacher, who lassoed Truly, who got into that list. Come on out and ask us some questions out in the hall, because we're using up the next crack's time. And we'll tell you about but we didn't tell you about one of the experiments of gravity. So we'll tell you about that out in the hall.